I did not. That would have been bad. But when our outcome is a count or a proportion, so for instance, are patients responding at the same rate under treatment A versus treatment B, where the outcome for each patient is yes, they responded, no, they didn't. The chi-squared statistic does the same thing as the t, only now I'm not going to get into the mathematics. Just know that the chi-square, just like the t, is comparing the observed rate of response to the expected rate of response. The observed rate in the sample versus what we would expect those rates to be if treatment didn't have an impact on how patients are responding. And then we standardize that by some measure of sampling variability. And so in essence, these two things are doing the same thing. It's a signal-to-noise ratio. So the bigger the value, the more evidence we actually have in our sample that there is additional variation in the outcome that can be attributable to the treatment. In other words, observed is very different from what we would expect if the null hypothesis were true. So if we go back to our example with LDL cholesterol, remember before we had the alternative hypothesis kind of described on the left. I've removed that because when we do hypothesis testing, we don't really compare our observed sample to the alternative. We only compare it to the null to see if we can invalidate or nullify it. So we have a distribution here that describes the kinds of sample mean differences that we're likely to observe if the null hypothesis is true. We're supposed to get something that's kind of here close to 0, but we could get things out in the tails. It's just unlikely. We also had 3 different scenarios, and this, I'm not sure why okay. It looks like things are off. So remember we had a scenario where we saw something way out here. It was a 15-point difference where we had an average for treatment A, 15 units lower than the average for treatment B. It was 125 versus 140. That gave us a 15-unit difference. It gives us a test statistic of 7.5. The other scenario was one that was actually very close to no difference. And that was a 1-unit difference in LDL. It was 140 versus 141. That gives us a test statistic of 0.5, which is a very small test statistic. So these are obvious reflections of how far away from what we would expect the observed data actually is. The kicker here, though, is this one that was not quite clear. It looked like it could have equally come from either of these, either the null or the alternative distribution. It results in a test statistic of minus 2.5. And so our question here is, what do we do with this? Do we reject the null hypothesis or do we fail to reject the null? For this t, it's pretty clear that we reject the null. Does everyone see that? It's far away. In fact, the way we interpret the t quantifies how far away our sample's observed differences are in units of standard errors of the mean. Does everyone remember what a standard error is? It's just a standard deviation. It's a standard deviation that describes the sampling variability or sampling error associated with our statistics. So just think of it as a standard deviation because we're used to those. If I get a t of 7.5 that's negative, then I can say my evidence is actually 7.5 standard deviations below what I would expect the evidence to show if the null hypothesis is true. And we know that that means it's really different, right? Because we generally think of plus or minus 2 standard deviations as being kind of the usual range of values. So it's way beyond that. This one is a half a standard deviation above. Not unusual, right? So we don't reject the null. We fail to reject the null. This is 2.5 standard deviations below. So if we had a rule of thumb of 2 standard deviations, we would reject it. But we're going to be a little bit more rigorous than that by actually trying to quantify the chances of this particular sample inaccurately depicting a difference when in fact there is no difference. So it's our chances, our observed risk of this being a false negative finding, and that's the p-value. The p-value tells me I have a 1% chance that this is actually an inaccurately depicting a difference when the null hypothesis is actually true and there's no difference there. So that's all the p-value is doing. Is that clear? So then we have to ask ourselves, when we designed this study, did we design it to do this test in a way that we're sufficiently powered for a clinically meaningful difference? If we did, if this is a designed study, then that p-value is valid. We should have also set the threshold for the maximum acceptable risk that we're willing to take on. Was it 5%? Was it 10%? Was it 1%? Was it less than 1%? And then we compare this observed level of risk, 1%, to whatever maximum risk we were willing to take on before we saw the data. Generally, that's 5%, but again, that's kind of an arbitrary rule of thumb that's just arisen because of historical precedents. It doesn't always apply, and you have to make sure that you think about what the consequence of a type 1 error is in the particular context of your study. You might want it to be smaller than 5%. You might actually want it to be larger than 5%, depending on what you're doing. So in summary, when we're comparing two groups, generally we have a continuous outcome and we're comparing average responses, or we might have a classification, categorical type outcome, and we're comparing response rates, proportions, if you will, between groups. Students T, chi-square. Those are probably the two most commonly applied methods that are unadjusted for other things. So all I'm doing with the students T and the chi-square test is I'm comparing responses or outcomes between groups. I'm not adjusting for other factors. If I want to adjust for something, I need to extend beyond these two simpler methods to a regression method. And the approach whenever you would have a student's T would be to do linear regression. The approach when you have a chi-square test would be to do something like logistic regression or ordinal logistic regression, where you're allowing the outcome to be categorical. Any questions about those two? I'm going to do a real quick an example of the chi-square test. So here we have an example looking at the relationship between cardiovascular deaths and surgery to the primary site in patients with cancer. So what they're reporting here are the percentage of deaths due to cardiovascular deaths and non-cardiovascular deaths. This is red and blue. By each of these conditions, surgery to primary site or no surgery. They've also given you the counts in the two groups. And so what we're looking at is there an association between the dependent variable, which is cardiovascular death within 1 month after diagnosis of cancer, that's a yes-no outcome, and the independent variable, or the predictor, which is surgery, yes-no. This is an observational study from the SEER registry. So again, because it's observational, people are not being randomly assigned to receive surgery. There's clinical decision-making behind whether or not a patient goes to surgery or not. That could be confounding any results that we see here. We would perform an analysis in this case using a chi-square test of independence, and the results from this paper state explicitly that using a chi-square test, they found that cardiovascular death was significantly more common in patients who underwent surgery than in those who did not. Notice that they report both the p-value, which says that the level of risk that this is a false positive finding is less than 1%. It's what? 0.1%. If I multiply that by 100. But they also give me a measure of the magnitude of difference that they see. So they estimated what the difference in those rates are. It's as big. Oh, I'm sorry. They didn't actually estimate the difference. They gave us the estimates for each of the groups. It's 12.3% in the surgery group versus 5.5% in the no surgery group. So we could do a comparison looking at risk reductions or relative risk to actually quantify the difference between those. The hypotheses that they're testing here, similar to the hypotheses that we had before, are whether or not these two interventions result in similar response rates or whether they result in different response rates. They're also interested in finding a difference in either direction. So we haven't really emphasized this yet, but I think this is a great place to talk about it. How do I know whether I want to do what's called a one-sided test or a two-sided test? So a one-sided test means that I'm interested in finding differences in a particular direction. I think it's going to be an increase. I don't care if it's a decrease. I think it's an increase, or vice versa. A two-sided test means that if it increases or decreases, I want to find either of those. So you have to ask yourself what your research question really is. What are the consequences of doing a one-sided test when you should be doing a two-sided test? Does anyone know the consequence of looking in one direction when you probably should be looking in two? Let's say you set up to do a one-sided test and you're looking for an increase, but the data shows you a decrease. What will be the conclusions of that hypothesis test? You're going to get a really big p-value, right? Because you're looking for an increase. You're not looking behind you, you're looking ahead of you, right? So you're going to get a p-value that reflects no difference. That's why it's always important to look at the actual differences that you see and make sure, oh my gosh, this actually resulted in a decrease. And then probably, if that's a meaningful decrease, or if you should have done a two-sided test in the first place, or maybe you have the direction off, then a two-sided test would have been more appropriate. It's more conservative, and it acknowledges that you don't know necessarily whether it will be above or below zero, or an increase or a decrease, but that both of those changes are meaningful to you. If only one of those changes is meaningful to you, then by all means do the one-sided test. It'll actually be more powerful. You'll get smaller p-values on the same data doing a one-sided test versus a two-sided test, just because of the way p-values work. Just make sure you pre-specify it and you really think through whether the one-sided or two-sided test is appropriate. For instance, if this was a design study, and right now the standard of care is no surgery, and they're trying to determine whether or not surgery should be used instead, probably a two-sided test would be appropriate. They might want to see a decrease in cardiovascular death. Well, this is cardiovascular death. Let's say it's death due to cancer instead. They might want to see a decrease, but they could potentially see an increase, right? Harm in that case, an increase in risk of death. So you have to be careful that you make sure you take into account what is going to occur in both of those situations that you flag, which are appropriate and meaningful using the framework of hypothesis testing. One other thing to mention, and I alluded to it at the beginning, that this is an observational study. These individuals received surgery because of clinical decision making, not because of some kind of random assignment. So if I were to read this study, understanding that it's observational, I would want to make sure it's not changing practice, right? It's generating hypotheses that should be looked at more clearly. But this would be considered a hypothesis generating study, not a hypothesis confirming study, because there are too many other potential sources of variability contained in the p-value aside from sampling variability, which is what the p-value is designed to quantify. Did you have a question, or you just...
Yeah.
Okay, sorry.
I just want clarification. When you say sided, a two-sided test, or the same thing as a two-tailed t-test?
Absolutely, yeah. So the question was, just in case people online can't hear, is when I say a two-sided test, is that the same thing as like a two-tailed? Yeah, that's what I mean. When you look in the tail of those distributions, two-tailed means like a non-directional test. If it's increase or high, decrease or low, I'm going to flag it. One-sided means I'm only looking in one direction. I don't care what occurs in the other tail, regardless of if it's big or not. Okay, so we've focused on two groups. We saw last week a single group. Now what happens if we have more than two groups, which happens a lot? So suppose we have, again, an independent variable that represents either exposure or treatment, And that independent variable has more than 2 possible values for all of our patients, all of our subjects. An example could be found in a study of smoking cessation. So investigators, public health investigators, are interested in ways to improve quit rates among smokers. Right now, all they're doing is educational interventions. So they're giving them literature, if you will, just pamphlets, and talking to them a little bit. They're interested in trying to improve quit rates because they think that this is not adequate, that there might be some improvement if they add to their standard of care either more information, behavioral therapy, or maybe even pharmaceutical therapy. So now we have an independent variable of therapy that has 3 different classifications. Subjects will be randomly assigned to one of these classifications, and then some outcome, this is a contrived example, some outcome that would measure their smoking behaviors is going to be recorded after 6 months of therapy to try to measure the benefit of each of these. The question really is, which of these is the best? So if we take a look at hypotheses of interest here, one potential scenario is that it's the current state of science, right? We're using the standard of care, which is kind of literature and a little bit of discussion. And we don't know that behavioral therapy will help or pharmaceutical therapy will help. So we don't know right now that any of these will show any improvement in the quit rates or their behaviors in terms of smoking in 6 months. So that's the null hypothesis, that the average, change in cigarettes smoked after 6 months is equal across all of these 3 groups: literature, pharmaceutical, and behavioral. If that's not the truth, well, then what is the truth? If I reject this null hypothesis, if I say that this is not true, then the implication is that at least one of these groups is different than the others. Potentially they're all different, but at least one is different if I flag that null hypothesis. So what would be an approach to actually statistically compare these groups in terms of their average smoking, if you will, after 6 months? Well, we already have the T statistic that we know can compare 2 groups means. I could compare the literature group to the behavioral group. I could compare the literature group to the pharmaceutical group. And then I could compare those 2 kind of experimental groups, the behavioral and behavioral and pharmaceutical group, to each other as well. So that's what's called all pairwise comparisons using the T. What's the problem? Well, I've already given it to you. What's the problem with doing a bunch of T tests? When I do a single T test, let's assume I set my type 1 error rate for the T test at 5%. What's the problem with doing a bunch of T tests? If I do a T test comparing group 1 to group 2, my chances of making a false positive finding are 5%. If I do a T test comparing group 2 to group 3, my chances of making a false positive finding in that test are 5%. I do it again for the third comparison, 5%. And if I go back to basic probability, what are the chances of making a single type 1 error, at least one false positive, if I've done 3 tests? We don't have to do the math. It's bigger than 5%, right? It grows. It grows as we do more. It's called multiplicity of testing. So when we do multiple testing, we are increasing our chances of finding something that doesn't really exist. And so we don't want to take that approach. That's an invalid approach. The proper approach is to apply a method that will still allow us to test those 2 hypotheses, flag a difference, and then go and look for the difference in the data. And that's the analysis of variance approach. It does the exact same thing that the t-test does, only it does not impact the type 1 error rate. So if I want to compare the average response across 2 or more levels of a categorical factor, I can apply ANOVA. In fact, I can apply ANOVA when I have 2 groups instead of the T. The difference between the T and the ANOVA is that the ANOVA uses what's called an F statistic, and we're going to talk about the F statistic in a little bit of detail because I think it's a really cool tool that's used frequently, and it's good to understand what the F actually conveys. One additional analysis that has to happen when you do ANOVA, again, the ANOVA table, the analysis of variance approach is testing these hypotheses. There is no difference versus there is at least one difference. Let's suppose I do the ANOVA test and the ANOVA test says reject the null hypothesis and conclude that there's at least one difference. I don't stop there, right? I want to know where the difference is. So then I can actually go and either generate confidence intervals on the differences or on the individual means, or I can do what's called post-hoc testing, which again are methods that protect us against finding things that aren't actually there. So the sequence is the ANOVA test. Is there a difference or not? If there is a difference, then I can go and generate post-hoc tests that tell me exactly where that difference is. As part of the ANOVA, you could also generate all of the confidence intervals, and then no post-hoc testing is necessary. You can just describe what you see. In ANOVA, you get what's called an ANOVA table. How many of you have ever taken any kind of formal classes that had ANOVA in it? So this is not a foreign concept to some of you. So the ANOVA table, all it's trying to do, if you remember back at the very beginning, I talked about the purpose of statistics is to try to attribute variation in a patient's outcome to different sources. Their sex, their age, their comorbidities, their treatment, the stage of their disease, and so forth. ANOVA is doing that. It's doing that in table form. So the variation in whatever the outcome is being explicitly attributed to different sources. And when I do ANOVA, there's only two sources. There's the treatment, and then there's that natural inherent variability in outcomes among patients who are treated the same. And so that's why ANOVA actually works, because it takes that idea of partitioning variation in an outcome and attributing it to different things. It takes it and actually quantifies it. So if you take a look in ANOVA, even though we're hypothesizing about means, it's using variances to make a decision. The mean square, this is why you gotta love statistics. I don't know if it's like this in your field, but in statistics we like to give so many different names to the same thing. Does anyone know what a mean square is? What's another name for a mean square? Variance. What's that? Variance. It's a variance. Why don't we just call it a variance? We don't just call it a variance because we want people to know when we say variance that we mean a variance from an ANOVA table or an ANOVA analysis, if you will. So we give, just like a standard error is just a standard deviation. So it gives it context. It's the same thing, but it has a different meaning, a slightly different meaning because of its context. So we have a variance and a variance that describe the variation in the outcome that's attributable to two different sources of the potential variation in the outcome according to the model. So one of the sources is that independent variable, X, which in this case is the treatment assignment. The other source, because this is output from R, it's called residuals. That's just error. It's everything that's unexplained, and it's lumped into one bin, and we call it error. It's that natural variation. And so the F statistic that you see in the ANOVA table, 22.64, is just a ratio. And we all know what ratios mean, right? If I have a ratio and it's really big, then that means whatever's on the numerator is much bigger than what's on the denominator. Ratios are never negative. The smallest they could be is 0. But they can be really, really big. They can go up and theoretically as large as infinity. So it's bounded on the bottom by 0, and then really big values indicate whatever's on the top is much bigger than the bottom. So this F value is a ratio of this variance to this variance. This variance is the variation in Y, if you will, between groups. So it's the variation, and you can think about it as quantifying the variation in outcomes between patients who are treated differently in this study. The variation here for the error is the variation within groups. And so it's quantifying how individuals treated in the same way or within the same treatment group, how their responses are differing. And so if there's no effective treatment, these two things should be about the same. right? The variation of responses between the two groups, if there's no effective treatment, it should be about the same as the variation of responses within groups. So you would expect to get the F value of 1. But if you have variation that's bigger across the different groups, that usually indicates that there's some kind of an effective treatment if your study, again, is well designed. And that's why the F statistic is a very cool tool, because it's just taking a ratio of two things, and it's interpretable. I can say that the variation between groups is 22.6 times as big as the variation within groups. That's a big difference. Do I even need the p-value? Not really. Just like I didn't really need the p-value for that t that gave me a 7.5 standard deviation difference. But the p-value here is very, very small. This is scientific notation because it had so many leading zeros it couldn't print. So this is a less than 0.01%. So again, the rationale, and I've already explained this, but I put it in words on the slide. That way when you come back to it in 6 months or a year, you'll have it written out. It's the rationale behind ANOVA and the F is that it allows us to look across many different groups to look for a treatment effect, as opposed to just focusing in on the comparison of two groups. It still can be applied to the comparison of two groups. Because of the way that it works, it controls or protects the type 1 error rate, and it's just a ratio of the variation across in patients' outcomes across all the groups compared to the natural variation of patient responses within groups. So let's take a look visually at some different scenarios that could result from a study like the one we're looking at, which is smoking cessation. So along the x-axis here, I've got 3 different scenarios, 1, 2, and 3, for each of the figures. And then inside each of these figures, I have a plot of the responses for patients who were treated by that treatment. So I've got treatment 1, treatment 2, treatment 3 in scenario 1. What you're going to look for here are obvious visual differences in how patients are responding on average. So there's an obvious difference in these scenarios. In scenario 1, can someone explain to me what I'm seeing? Am I seeing a treatment effect in scenario 1? Yes, right? This is the raw data. This is not a confidence interval or a standard error. This is the raw data. When I do a standard error, it's going to tighten those things up. So that if I look at the distribution of responses, I see group 1 has a lower response overall than patients in group 2 and patients in group 3. So I can see not only are the averages increasing, but the distribution itself, the distribution of responses is increasing across the groups. What about scenario 2? I still see that the average, which is represented by this dark line, that's increasing, right? Low, a little bit higher, a little bit higher. But what about the variation within the groups? What's going to be the problem with analyzing this data within ANOVA? Think about the two sources of variation, the variation across and the variation within. Do you think the variation across all the groups, the numerator of that F, is going to be big enough to overcome the variation within the groups? Maybe not. This will be one of those, I really need the hypothesis test here to tell me. I think 1 is clear, 2 is not so clear. What about 3? 3 is pretty clear as well. That's the null hypothesis. Visually, there's no difference in the averages. One other thing that I find meaningful here is that not only do these box plots tell us about how things are changing on the average, they also allow us to visualize the variability. One of the assumptions of both the T, that's comparing averages between groups, and ANOVA is that the variation within the groups is approximately the same. And you can see now with the F why that's important, because that is actually the thing that makes up the denominator of the statistic. It actually made up the denominator of the statistic for the T as well, but we didn't emphasize it there like we are here. So if I actually have different within group variation depending on the group, then that invalidates this test. In 3, I see that there appears to be some problem with the variation, but there are rules of thumb for that, and you can actually also do hypothesis tests to verify that assumption. So again, for the F statistic, it's a variation, it's two variances. In the top, you have variation in outcomes across the groups or between groups, and on the bottom, you have the variation within the groups. And if F is big, then that means that the numerator is much bigger than the denominator, and we have evidence for more variation in the outcome than across groups than within. If F is close to 1, that means the numerator and denominator are very similar, and there's not really evidence that there's additional variation in patient outcomes as a function of treatment. So then in that case, I would fail to reject the null hypothesis. So let's take a look at the F, again, back to the ANOVA table. So now I hopefully, I'm not going to get into degrees of freedom or sums of squares, but the mean square, again, is just quantifying variation attributed to different sources. If you take a look at how big each of those are, they all start at 0 and they go to infinity. So you can take ratios of any of these sources of variation and describe how much bigger one is than the other. When you get a more complicated ANOVA model, you might have more sources of variation in here. Maybe I have treatment and sex, and maybe their interaction. So this could become a much more complicated ANOVA table, but the mean squares have the same meaning. The p-value then reflects the observed level of risk that this is a type 1 error, a false positive finding. So we have an F that reflects variation between groups that's almost 23 times as big as the variation within groups. It's not surprising that the risk that this is a type 1 error is basically 0. It's a huge effect that we see here. And so the conclusion is that you reject and state that there is a difference somewhere. The problem with ANOVA by itself is we don't know where the difference is, so we have to then go and generate, I prefer actually, generating confidence intervals on the mean differences. What's the difference in behaviors or in outcomes between group 1 and group 2, the difference between group 2 and group 3, and so forth and so on. But you can actually perform tests like Tukey's test, which does all multiple comparisons. And this will actually give you what I just mentioned, which is the confidence interval, a 95% confidence interval adjusted for doing all of these tests, along with a p-value that really is doing that pairwise test, mu1 versus mu2. So I can see here, I can't remember now, A I think was the standard. Is that true? A was literature, B was behavioral, and C was pharmaceutical therapy. So if I go back to this information, I can see all those pairwise comparisons, A versus B, A versus C. So this is like experimental therapy 1 versus standard of care, experimental therapy 2 versus standard of care, and then is there a difference in the two experimental therapies? So I can focus right away on the p-values, and I see they're all very small. The least small is the one that compares the two experimental therapies, but then I might want to really just put context to those p-values. I can look at the difference. What's the estimated difference? And so they've quantified it here by the outcome. The average difference, the difference in the averages is about 6.6 units, and I think this is like cigarettes smoked. So there's about a 6.5 unit difference between behavioral therapy and standard of care. There's almost a 12 unit difference between pharmaceutical therapy and standard of care, and just a 5 unit difference between the two, behavioral and pharmaceutical therapy. And then, of course, it's important to acknowledge that there's uncertainty with those estimates, and so you get a lower bound and an upper bound on each of those estimates. Any questions about the ANOVA? I have a conclusion here about kind of how it would be written up, but we'll move on because I think we have time to get to some other things. So again, inferences on means can be done generally with T, but ANOVA will always work as long as you can verify the assumptions of normality of the outcome and equal group variances. Just that would be verified, I think, both ways by just doing those box plots. It's pretty adequate. The problem with ANOVA, for any of you who have taken a class in ANOVA, when we're trying to partition sources of variation into different bins, partition variation and outcome into different bins, there's not always just a single factor that could explain the variation in the outcome. And there are many different ways in which multiple factors could interact to produce an outcome. So there are many, many, many different ANOVA models. This is a partial picture of some of the models that correspond with different kinds of designs, whether they're experiments or observational. So if you get much beyond kind of a relatively simple experiment or analysis, you probably want to just consult briefly with a statistician to make sure that your model is appropriate and is actually accounting for the things that you want it to. Let's do a brief example when we have, so if we have more than 2 groups and our outcome is categorical, again, it's a chi-square test. Here's an example of that. It's analogous to what we just did. We had 3 treatment groups, and we had a continuous outcome that we wanted to compare. So naturally, it made sense to compare the average response of that outcome among the 3 treatment groups. Here we have 2 treatment groups, but our outcome is no longer continuous, it's categorical. So I have 2 different treatments, A and B, and this is a cancer experiment where I'm looking at a patient's tumor response according to imaging as a complete response, a partial response, stable disease, and failure. And so since I have this kind of categorical or ordinal outcome, I generally present that data in a contingency table. So what you see in each of these cells are the number of subjects in my study of 300 who received that treatment and responded in that way. So 32 out of 100 who received treatment A were complete responders. 55 out of 200 who received treatment B were complete responders. And then I could look at the failures as well. 9 out of 100 and 16 out of 100. So the question that we have here, it's really the same question we had before. Do patients who were treated differently respond differently? And in this case, we're not comparing means. We are technically comparing proportions, but what we're looking at is a test of association. It's a chi-square test of independence. And we're just looking for differences in the way patients are responding in these 2 rows. So we're going to compare the observed frequencies, the observed counts in those cells to what we would expect them to be if there were no treatment effect, in the same way that we did it with the t-test and the f-test with continuous responses. The only rule of thumb here, for the T and the ANOVA, we have to verify normality. We have to look for outlying observations. We have to make sure that the group variation is equivalent. Here we just have to, again, focus on sample size. What we don't want to see is an empty cell, meaning a count of 0. What we really don't want to see is a count less than 5, and that's all that this means right here. We don't want to see, well, we don't want to see 0 counts, but we also don't want to see what are called expected counts less than 5, which is, I'm not going to get into that actually. Just know that you need to have sufficiently large samples to do this. If you don't have it, you can always default back to something that doesn't have a sample size restriction like Fisher's exact test. And that, again, it's a non-parametric. It's an exact test, so it gives you an exact p-value, regardless of what the distribution of responses is. So the hypotheses that we're comparing here in English is that patient response is independent of their treatment versus it's not independent or it's associated with their treatment, either increased response or decreased response. We could also state this in terms of those response rates, the proportions, but there's no need. What you're really doing is you're looking at, are patients responding in a way that we would expect if there's no effective treatment, which is what I just said there. So if we take a look at how we do this, if you remember the formula for the chi-square statistic, it was a sum of observed counts and how they differ from expected counts, standardized by some measure of sampling variability. So the way the chi-square statistic works is I make an assumption that there's no difference, and then from that I can actually calculate what I would expect to see in terms of patient counts in these bins, and then I compare those expected counts. I subtract them from what I actually observe, standardize it by the count, and then add up all those deviations. And so if I get big differences, they add up to even bigger differences, and I get a big chi-square. So again, it's working in the same way, the T and the F are, and I end up with a 7.815 here, which is a relatively large value, but if we plug that in, if we plug this data in and get that, we can see that the p-value is about 0.029, which indicates that the risk that this is a type 1 error, the observed risk that it's a type 1 error, is less than 3%. If our threshold was above 3% before doing the analysis, then we would reject the null hypothesis and state that response does appear to be associated with treatment. One other way to visualize the data, if you remember from the very beginning of the slides today, I had a figure where we had treatment and control on the as defining rows, and then we had the type of response defining columns, and then the boxes within those treatments reflected the relative frequency for each of those outcomes. That's a good way to visualize it. You can also visualize it using bar charts. So this is a very simple bar chart where you color code the type of response, and along the y-axis you represent either the frequency, the count, or the percent of patients in each of the two groups, A and B, who responded in a certain way. Briefly, we're going to talk a little bit about a different, unique kind of outcome. So I've focused so far on categorical data, categorical outcomes, like yes-no outcomes, or the ordinal complete response to failure. I've also focused on continuous outcomes. There are other unique kinds of outcomes that actually, in a single value, quantify both categorical and continuous information. And those kinds of outcomes tend to come to us from survival applications. So survival data is unique in that it has both a continuous component, which is the time it took a patient to achieve some kind of outcome or event, and it also has a categorical aspect to it, because sometimes patients respond, sometimes they don't, and sometimes we never see the event happen. So we have a yes-no and a timing or continuous component together. So we can't apply the usual methods. We shouldn't apply t-tests to that kind of data, and we shouldn't apply chi-square tests to that kind of data either. We want to maximize our ability to find differences in that kind of data by using methods that were designed for that combination of continuous and categorical. So the kinds of questions that we often ask when we look at survival analysis revolve around, and I'm going to stick here for just a moment to the idea that death is the event of interest, but survival analysis can be applied in any scenario. Death doesn't have to be the event. It could be progression of their disease. It could be resolution of their disease. It could be they crashed a car. I mean, it really could be any event where you have the ability to measure from some predefined origin point to the timing of the event. It's applied all the time in insurance for like risk management, for instance. If I insure this guy, how long is it going to be before he crashes his motorcycle? What are the chances he's going to crash his motorcycle in the next 6 months? That kind of thing. So it's applied universally when you have this kind of data. But we very often see in biomedical research, we are interested maybe in looking at the time from the moment a person is diagnosed with a disease until their death. And so that's what's represented here. Along the x-axis, we start with 0 when we go out to 96 months. Along the y-axis, we have a measure of probability, which is really the chances that a patient will live to that point if they've survived that long so far. And so the kinds of questions that we ask revolve around what are a person's chances of surviving for a year past some kind of diagnosis? Or what's the average time individuals with this diagnosis survive? Likewise, we could be asking questions like this as it relates to different kinds of treatments and instead of diagnoses, so it can be applied universally. So this class of methods generally are referred to as survival analysis methods. They again study both the occurrence and timing of events, and although we generally think of it in terms of studying patterns of death, it can be applied to many different scenarios. For instance, I've done survival analyses on time to rehospitalization, time to quitting smoking, time to response, time to progression, time to development of a disease, and so forth. Some of the things that we tend to report in time to event, we might report something like 5-year survival or 1-year survival or 6-month survival, whatever is a meaningful time given the context of the research. So 5-year survival, when you see this reported, it's just simply a percent. It's the percent of patients that are still alive 5 years after treatment begins or 5 years after diagnosis. And again, it doesn't have to be 5 years, it could be 1 year. But it's just a measure of prognosis of disease. It's a measure of prognosis for individuals receiving different kinds of treatments with a particular condition. We also generally talk about survival in general, and that's the probability of remaining alive, if you will. I say, quote, alive if we're talking about death, for a specific length of time. And that survival is estimated across all units of time. And that's what you see when you see those Kaplan-Meier curves. You're seeing the probability of remaining alive at each given point in time. A unique feature of survival analysis type data is that we have something called censoring, which is just a unique kind of missing data. Observations or patients' responses are censored when we have incomplete information about their survival time. So for instance, if you're doing a study and it lasts for 5 years, you're giving different kinds of treatment and you're following everyone for 5 years, there will be some patients that are still alive at the end of your study. You're not going to get complete 100% of the individuals dying during that 5 years. So it turns out if they didn't have the event of interest in the observation period, they are censored. That's actually missing data because you didn't see the event occur and you don't know the timing of that event because you haven't followed them long enough. So another circumstance where censored data might play a role is when we have loss to follow-up. In these longer longitudinal studies, you might actually lose track of individuals. This happens a lot in observational studies where you're going back to EMR data and you're pulling different records, different imaging records to see when a patient's disease progresses or when they die. They might have moved away from Kansas City, so they're no longer in your system. They might have gotten treated elsewhere. So all you have is their date of last contact, and that's when you censor them. Only subjects who are still alive at the end of a termination date will have a censored value at the end of the study. Otherwise, if they were lost to follow-up, they'll be censored somewhere else and they'll have incomplete time information, not the same amount of follow-up. But if you have in your data set, in your study, if you are able to observe the event, whatever it may be, happen in everyone that's in your study, you have what's called a complete set of data. And I don't think in the 10 years that I've been doing survival analyses that I've ever had a survival analysis where we didn't have censoring. So it very often doesn't happen that way. Censoring, again, can occur in many ways. Here I have an example of 4 different patients. This is time 0, this well-defined origin point. And then we're following them out to 12 months. At 12 months, my study ends and I'm not allowed to watch them anymore. I can't see what happens beyond 12 months. But I can see that subject A did not have the event within the 12-month window. So for subject A, the time that I record in the data set is 12 months, and then I also record a flag that they were censored at that time. For subject B, I was able to follow them almost to 12 months, and then they had the event. So in the data set, I have that time, which is like 11.5 months, and then I flag them as having had the event. That was a death. C, notice it doesn't have the star. This person was censored at about, let's say, 9.5 months. So I record the value. I know they were alive to 9.5 months. That's the timing. And then I have a flag for censoring. They were censored. I did not observe the event occur. And then D, even though D never has the event, whatever it may be, D's information, the subject D's information is actually identical to subject A's within the study window. They both contribute 12 months of event-free information to my study, even though one has the event right after the 12 months and the other one doesn't. Survival functions, which are most often reported using the Kaplan-Meier method, are probably the most common way of visualizing and comparing the idea of survival between groups. And again, the survival function, which Kaplan-Meier is estimating, is just it's conditional on time, and it represents the probability that individuals in that population will survive longer than a particular time t. So if we take a look at Kaplan-Meier curves here, along the x-axis we have time since transplantation from 0 to 8, and along the y-axis we have melanoma-free survival. So at time 0, everyone is alive, which is why both of these curves are up at 1. But as we move forward in time, we start to see more deaths. And so every time we see a death, the curve drops, because that empirically tells us that there's some risk of death associated with this particular population that is occurring in a certain way over time. If we have no censored observations, then this is an exact proportion. But if we have censored observations, it's not quite that. Another way of reading this graphic, the rate at which these curves are descending is sort of a measure of the risk of death for any particular time window. So the more rapid it's descending, kind of the higher the risk of death. And it might eventually flatten out, and that tells you that people are not dying as frequently, and so the risk is kind of leveling off at some point. When we talk about risk of death in the context of survival analysis, we generally try to describe that using something called a hazard function. These are less reported than the survival functions. We do sometimes compare hazard functions through something called a hazard ratio, which we'll see in a moment. But the hazard function is a way of describing almost a risk at a particular point in time. So this function, if you see here, is representing the chances of dying at a particular point in time if a patient has lived up to that point. We often compare hazards, for instance, in maybe two populations or according to maybe some measure of disease severity, or even for different treatments using a hazard ratio. Has everyone here heard of the hazard ratio at least? It's like a risk ratio. The hazard ratio describes kind of this risk of dying in one group compared to some control. And so in English, the hazard function represents the proportion of patients dying at a particular point in time. And the hazard, risk can occur in many different ways. It can occur like this, where you have higher risk early on that decreases over time and then actually starts to increase again. You can have risk that starts high and then decreases over time. You can have risk that starts low and increases over time. But the idea here is, if we want to compare kind of this instantaneous risk of the event between groups, we actually have to take ratios of this hazard function. A couple of last things. If you need to leave, you can go ahead and leave, but I want to try to fit this in because it's a natural stopping point for next week. Here's an example with regards to the flu. Sometimes these hazard functions are not very easily interpretable, but we can make them interpretable if we do a little bit of mathematical manipulation to them, if you will. So suppose I'm looking at a population and I calculate the hazard for contracting the flu, and I'm measuring time in months, and I get an estimate of the hazard of 0.015 in this population. The interpretation of that is that I can expect, if I'm a member of this population, I can expect to contract the flu 0.015 times per month, because month again is the time unit measure, assuming my risk over time stays constant. But the 0.015 times a month doesn't make sense, but guess what? I can multiply that out until it does have meaning. If I multiply that out by 12, I can get the number of times I can expect to get it in a year, 12 months in a year. And if I multiply that value by 10, I can get the number of times I can expect to see it or to get it in a decade. So it's a good way of describing, kind of in an epi perspective, how frequently you can expect as a member of a population to have something happen. Cumulative hazard describes kind of how things accumulate over time. Here we have an example of time on the x-axis and a hazard of epilepsy. And what you see is at the beginning everyone is disease-free. And then by treatment it starts to, not by treatment, but by group, some of it defined by treatment, some of it defined by a condition, it starts to separate out. And we can see that increasing incidence of events. So the green line increases faster and ends up at the top higher. That tells me that events are happening more frequently in that group than they are in the other two groups. And it's, again, cumulative hazard is describing the probability that an event has occurred by a particular time in a population. So depression treatment, and this is diagnosis essentially of epilepsy, and you can see it's increasing over time. And by 10,000 days, about 20% in that group have it. Hazard ratios are a way of comparing, quantifying effect sizes in survival analysis. They represent how much more or less the event is to occur in one group relative to a control over a well-defined period of time. So like the risk ratio from earlier, a hazard ratio, if it's equal to 1, that indicates equivalent event rates or equivalent risk. But if I have a hazard ratio greater than 1, for instance 1.1, that tells me that the rate of the event is 10% higher during the observation period in that numerator, the treatment group, than it is in the control group. If I get a value less than 1, then that shows decreased event rate over that unit of time. The way that we compare survival curves or survival in different groups generally is the log rank test, which is just comparing the survival functions and seeing are they different at any time over the observation period. If we want to adjust for multiple factors simultaneously, there are regression methods as well for survival analysis, like Cox regression, which we'll talk about next week. One of the important things about survival analysis, since you are capturing risk and event rates over time, anytime we have longitudinal observation, it's always a risk that things are changing in our patient population or in our subjects over time that could be impacting how they're responding. And that's called a time-varying covariate. An example of that would be if you were evaluating the effect of oral contraceptives on stress fractures in women athletes over 2 years. The problem with this kind of study is that women might be switching on or off of the exposure. So exposure is changing over time, which would impact your ability to see any association between oral contraceptive use and stress fracture. So if we could incorporate information about when women are starting and stopping oral contraceptives, we can incorporate that as a time-varying covariate and actually tease out the impact of oral contraceptive use on risk over time. And then this type of analysis is really only seamlessly performed when we have this kind of survival type of data. I'm going to stop there because we're right at 11 o'clock. I want to mention that next time we're going to focus primarily on regression methods pulled from the literature. in observational and experimental studies. And we're also going to talk about the importance of and the methods for power and sample size estimation. Any questions? I know we went through a lot, so yes.
So it's just about the p-value. I feel like I've almost always seen p-value less than 0.05.
Mm-hmm.
What are the guidelines when a lower or a higher value should be used?
Okay, so the p-value, the question is the p-value, you generally most often see the cutoff at 0.05. And I think that it's a reasonable cutoff, right? It's like a 1 in 20 chance of it being a false positive finding. And we tend to like those nice kind of rigid structures for performing experiments because it minimizes the need for us to make kind of subjective decisions about what the design should be. I would say that the easiest example to convey that that's kind of an arbitrary cutoff point is in drug development. So if we think about, let's say we're developing a drug for a really horrendous cancer that doesn't have a lot of good standard of care right now. I always revert back to pancreatic cancer because that sounds like a horrible, it sounds horrible. Pancreatic, liver cancer, those kinds of things. If there's not anything that works well now, if the standard of care is really not that great, I have to think about, if I'm doing research in this area, the consequences of errors in my research. So the consequence of, let's say I'm a basic scientist. So I'm doing things right before they get into the clinic, first in human. I might be doing animal studies. The consequences of having a compound where the truth is that compound will make an impact. It might incrementally improve care or it might greatly improve care, but regardless, it would be an improvement over the current standard of care. I don't know that, but let's assume that's the truth. The consequences of me testing that and failing to find that difference and then shelving it, in my opinion, are much greater than that compound not really being the breakthrough and me pushing it forward just in case. Does that make sense? So both of those would be errors. In one case, it's effective and I fail to find that. In the other case, it's ineffective and I falsely say that it is and I move it further into development. Both of those are bad things, right? So we should always try to control both of the risk of both of those errors occurring. But I might be more willing to live with one of those than the other because the long-term consequences of shelving a beneficial drug are, in my opinion, greater than wasting money on a study, a smaller study to say, oh, this really doesn't look like it's going to work and we'll shelve it. You know what I mean? So if we reflect the consequences of errors and how they are actually handled in drug development, when we start early, the importance is not really on the type 1 error rate. It's kind of relaxed, if you will. If I'm doing a phase 1 study, I'm not really tightly controlling my chances of errors because I want information. I want these hypotheses to pop. I want to generate them and gather information to be able to inform the design of a really good study to try to confirm that there's no harm or no additional harm and some benefit. So I might be looser with my error rates early, but as I'm building my scientific knowledge, I'm tightening them up. And so when I get to that phase 3 study where now all of a sudden if this study says there's something there in this compound, it's changing practice. People are going to stop treating with the current standard of care, and they're going to start treating with this therapy. Now let's think about the consequences of an error there. That's when your type 1 error rate needs to be really small. So we tend to see the control of type 1 error increasing the closer that thing gets to getting into the clinic. Does that make sense? There are times when the type 2 error rate is more important, and I would argue that that's kind of early on. You really want to find things and not reject them outright and put them back on the shelf because you're too stringent in your error rates. Any other questions? Okay, next week we're in here. So she told me it's in lead. So I'll make sure that I send that email out to clarify, because I think on the flyer it says clendening for all 4 weeks. All right, thank you all. It is. Let me turn it off.